Welcome to lecture number 12 for ECE 461-661 control systems, block diagrams, and Simulink or Bism. Now, a little bit of background on this. I used to work at GE Aircraft Engines, and there we would model jet engines using a Fortran program. And the saying at the time is that only God and the person who wrote the program understood it, and we weren't too sure about God. When some of these programs came out, like we're going to be talking about Bism, Simulink, we were all excited because now you can actually graphically describe how the dynamics of a jet engine worked, how the software worked, so it'd be much easier to understand, and more importantly, easier to maintain, easier to debug. So you could sit there and describe a jet engine with these different transfer functions. Each side of these I would double click, expand it out, showing how this part is modeled even more detail, double click again, expand that out, get that even more detail. I would have these models that I could test, I could debug, I could understand, I could maintain. So likewise, we were really excited when these programs, Bism and Simulink, came out. We still use them in this class. In control systems, it's a really nice way to describe how a system behaves. And then using graphical interface, I could just drag and drop, connect components together. And more importantly, when you do your homework and I do my analysis and say, I think this controller is going to give me the response I want, this is the way you can test it. I can sit there and build the system and try it and see, do I actually have a settling time of 4 seconds? Do I have 20% overshoot? It'll do other things as well. I can sit there and add nonlinearities, add noise, add a discrete time system combined with an analog system. Bism and Simulink will do all that. So likewise, these are used extensively in the industry for testing your designs. So today we'll cover a block diagram, how you describe a system with these blocks, what they mean, how to simplify them, how to come up with the transfer function from the input to the output, and then how to build them using Simulink and Bism. So starting out, some of the definitions and symbology. In block diagrams, I've got these arrows. That's the direction of signal flow. A feeds into Y, not vice versa. A circle is a summing junction. And if there's a minus sign, that means subtract. So this would be A plus B minus C produces Y. That's a summing junction. Rectangle is a gain. This would be the output Y is gain times input, Y equals G times X. The gain could be a scalar, or it could be a transfer function, meaning a differential equation. If I cascade blocks, I can simplify it. Here, Y is G times A, call that dummy variable. A is K times X. Put it all together, Y is G times K times X. And notice when you find the transfer function, you kind of go backwards. The output is the first one, G times K. In general, G and K could be matrices. Matrix multiplication is not commutative, so G times K is different than K times G. In this class, we're dealing with scalars, so you can get away with it in this class. You can be a little bit sloppy. For scalars, G times K is K times G. But technically, it should be G times K. In parallel, if I have a signal split apart and then re-add, I have Y is G1 times X plus G2 times X, or the net result is the overall gain is G1 plus G2. That's series in parallel. The one we're going to be using over and over again in this class is feedback. If we have this system, it gets a little more complicated. I can do that by assigning a dummy variable at the output of the summing junction and say Y is G times E. E is X minus Y. Now do some algebra, substitute for E, solve for Y. I get Y is G over 1 plus G. We'll be using that over and over again in this class. The gain of a feedback loop is G over 1 plus G. And this is where you get problems. I can have a perfectly well-behaved system G, but if the gain ever becomes minus 1, I get a gain of G over 1 minus 1, gain becomes infinity. That's where you go unstable. That's kind of like at a rock concert. If you're at a concert and they crank up the volume too loud, I get this horrible screech. What that screech is, at some frequency, the phase shift adds in phase. So the signal going from the speaker through the air, to the microphone, to the amplifier, back to the speaker, adds in phase. If the gain at that frequency is bigger than 1, I get a gain of 1 plus 1 plus 1 plus 1. The signal builds on itself, goes to infinity. that's where you get that screeching. There's only one frequency where the signal adds in phase. If the gain of that frequency is bigger than 1, you get your screeching, the feedback. That's unstable. Again, that's a feature in this class. I can take a perfectly well-behaved system and make it go unstable. The trick is, how do I design it so that it's stable and meets my design specs? So if I have a block diagram and I want to solve for the transfer function, there's a couple ways to do it. The first approach always works. It's assign dummy variables to each of the nodes, write n equations for n unknowns, then solve. Now, that can take a while. There's a shortcut that almost always works. It's the gain from the input to the output in the numerator over 1 plus the loop gains in the denominator. I'll show you when that doesn't work, but almost always that does work. For example, here I've got a feedback system. Find the gain from R to Y. Well, one approach is to find dummy variables at each of these points, and then write out the equations. I now have 1, 2, 3, 4, 4 unknowns. Write 4 equations for 4 unknowns. Y is G times U. U is K times E. Equals R minus W. W equals H times Y. Now substitute and solve. Takes about 20 minutes. I'll get GK over 1 plus GKH. That's one approach. Second approach is to use the shortcut. I can say it's the gain from R to Y, and here's the only one path, G times K. I can't go backwards through the arrows. I have to go in the direction of the arrows. So that's the numerator, GK. 1 plus the loop gain. Here's the one loop. The gain around the loop is G times K times H. So the transfer function is GK over 1 plus GKH. Second example. This one's a little bit trickier. Find the transfer function from U to Y. Again, there's a couple ways to do it. One approach is to find all these variables. That gives me 1, 2, 3, 4, 5, 6. 6 unknowns. I need 6 equations for 6 unknowns. That should be Y equals C times D. D is B times C. C is B minus E times Y. B is A times little a. A is U minus D. Solve, about 20 minutes later, I get a transfer function. That's one way. A little bit easier, if you just define the summing junctions as your output, that also works. That's a little bit easier. Here I only get 3 equations, 3 unknowns, which is way better than 6 equations, 6 unknowns. In this case, I would get Y is C times B times little b. Little b is minus D times Y plus A times little a. And little a is U minus B times B. 3 equations, 3 unknowns, substitute and solve. I get the same answer. Third approach. Way easier. The numerator is a gain from U to Y, and there's only one path. It's just going to be A times B times C, and I could do this loop in here, but that's going to show up in the denominator. So you just get that path over 1 plus the loop gains. Here's one loop right here, A times B. Here's the second loop, B, C, D. So the denominator is 1 plus AB plus BCD, and sure enough, that's the right answer. And kind of a check, you might be wondering, well, why don't I do this path? A times B times A times B times C? Well, it's whatever gets you the right answer. From before, this approach always works. The numerator is just ABC. So the shortcut is, once I get to the output, the path to the output without going through these loops. Those loops will show up in the denominator. The numerator is just A times B times C. Kind of some background. If you're going to take the FE exam, the last couple of years, all they ask about in control systems are block diagrams. So if you just memorize the numerator, ABC, over 1 plus the loop gains, you'll get most of the FE questions on control systems. There is more to do in controls, so we're not done with the course right now, but that's typically all they cover in the FE exam. I mentioned this usually works. Where it doesn't work is if I have two systems cascaded. For example, if I had this system cascaded twice, I would think that the gain would be 1 plus GKH times 1 plus GKH, which would give you 1 plus 2 times GKH. That's actually not correct. Take these two blocks and cascade them. What I'll get is this gain squared. And when I square it, I'm going to miss a term. So if you have two systems cascaded, the shortcut that I talked about doesn't work. Instead, if you have two systems cascaded, solve each one separately, then multiply the two answers together, then you get the right answer. So that's kind of block diagrams. Bism and Simulink. Bism and Simulink are graphical tools that make your life way, 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 way easier. It's a nice way to graphically describe how a system behaves. Simulink is part of MathWorks. You should have them on every computer at NDSU with MATLAB. NDSU has a site license for both MATLAB and Simulink. If you get MATLAB on your own, again, you can download MATLAB, get MATLAB, go to the Control Systems webpage on Bison Academy, go to Resources, and here we go. This is a link to NDSU's license. You can request a license for MATLAB and install it on your computers if you're an NDSU student. Simulink is also available. If you just do a search online, you can find Bism. It predates Simulink came out in 1991. It's available online for free. It's intuitive, friendly to use. There is a user's manual. I personally have never read it. You don't need to. That's kind of my preference. For example, what Bism does, again, these will be examples in Bism. Simulink will look almost the same. I can sit there and draw these block diagrams and say, here's the first system with the feedback loop. Here's the second one, comes in. Here's the third one. Kind of the same way you draw the block diagram. Here's a plot. Now find the step response. Bism will do that. To use Bism, again, Simulink is easy, but very similar. Just use the pull-down menus. For example, let me show you. This is what Bism looks like. If I go under block, again, there's the user's manual. I just kind of scroll down until I find what I want. Here's a transfer function. Suppose I have 100 over s squared plus 3s plus 10. It goes in decreasing powers of s, same as MATLAB. If I want to find the step response, that's a signal producer step, and just drag and drop. To look at the output, this is one that's kind of hard to find. It's a signal consumer is the plot. I've got different types. I can get numbers, lights getting brighter and dimmer, strip charts. Plots are really the main one I use. And I personally hate the colors of the plot. If you're an Iowa State fan, they're nice colors, but being NDSU, we prefer green and yellow. So let's change the appearance. Let's make the background white. Override the default. Foreground black, sure. Connect that up. I can now find the step response. That's either right here, go F5, or if I want to change the default, simulation properties. I typically make the step size 0.01. The smaller the better. Typically, if I go too small, it takes a really long time to run. Let's run it for 5 seconds. And if you go under integration methods, here's the different types of integration available. I've got Euler, that's the simplest and worst. As you go down the list, you get better and better integration schemes. I kind of like the fourth order Runge-Kutta. Again, kind of a matter of taste. Now if I hit run, there's your step response. I can do things with Bism, such as let's have a feedback. Let's add another linear system. Let's make this an integrator. 1 over s. add a summing junction. Connect those up. I want to have a feedback loop coming down here. This annotation, there it is. And let's flip it. Edit, flip horizontal. This just makes it look prettier. And if I do, this is one that's actually not well documented. I do Control, right click, I can change that sign. Here I'm using negative feedback. I can sit there and see what happens. Here's my negative feedback, and I just went unstable. Again, change the gain. Let's try gain of 0.3. And I've got an oscillator. Some ways to simulate it. What Bism will also let you do is I can mix analog and discrete. I can sit there and say, this is a discrete time system. Sampling rate is 0.1 second. And the Z transform will be Z minus 0.9 over Z minus 1. Kind of notice, if I take this off, it thinks that's continuous time. If I make it discrete, there's a Z. Z means discrete time. And probably the gain is too large. Let's make this 0.01 and 0.1. I can now simulate. Okay, that was way too big. Yeah, it's still unstable. If I take this arrow over here, I can now see the input changing every 0.1 second. As I did wrong. Changed the wrong term. And the input changing every 0.1 second. And you see those little stair steps. Those stair steps are your discrete time system. The input only changes every 0.1 second. So I've got a mix, a discrete time system, Z plane, an analog system, S plane. Bism can handle that just fine. A little bit harder on analysis because I'm mixing planes, but this is how systems are actually built. I'll have a microprocessor in the Z plane, a motor in the S plane. How do the two work together? Bism can do that. Did that. On your homework. In this class, each homework problem has multiple solutions. The real acid test is if it works, your answer is correct. What I ask is that on your homeworks, if you want to check your answers, throw it in Simulink or Bism. If you do a screen dump and say, here's my plant, here's the controller that I designed, here's the step response. If it meets the requirements, such as a 2-second settling time, 20% overshoot, you did it right. That's a valid solution. It's a way to check your answers to see you're doing it right. It makes grading a whole lot easier. Again, all I have to do is look at the graph. If you got the right graph, you did it right. And it's a nice way to check, are you doing it right? Again, if the Bism response doesn't match up with your analysis, there's probably something wrong with your analysis. So that's lecture number 12 for ECE 461 Control Systems, Block Diagrams.